This problem goes along with 4.7 electronic homework in my open math, number 8. Different numbers, but it's the same process. We can't just use base E because it's not continuous growth. So we are going to figure out what our base is. We have information given to us that we can plug in. So I've done that here. The count in a bacteria culture was 600 after 15 minutes. So that's this first equation, 600 equals A, B to the 15th. And 1300 after 30 minutes. So I have this one over here, 1300 equals A, B to the 30th. Now a neat thing, not only can we, subtract polynomial equations like we've done before, you've done that with systems, or subtract them, you can actually divide them. So you can add, subtract, multiply, and divide equations. So that's a nice little quick way to do this. So I'm going to take this second one, just so I end up with a positive exponent there, equals A, 1300 equals A, B to the 30th. And I'm going to divide that all by 600 equals A, B to the 15th. And then what happens is these A's reduce. So what I'm left with is going to be 1300 over 600. We'll reduce that in a minute. Equals B to the 30th over B to the 15th. So that would be B to the 30 minus 15. So that gives me just B to the 15th. So the 1300 over 600, I'd want to reduce out those zeros, and I'm going to get 13 over 6. Now to solve for B, I need to raise each side to the 1/15th, or take the 15th root. When I do that, if I estimate on a calculator, that's not going to give me as accurate an answer as if I just kept it in the fraction form to the exponent. But I am going to write what the approximation is here. So you want to really try to keep it in the fraction if you can, because that's an exact answer, but it comes out to be about 1.05289, so on and so forth. So if you do round it all, make sure you go out probably about 4 or 5 places, and then you won't get too much rounding error, and it should come out the same. But if your answers are consistently just a teensy off, let me know, and I can help you with that. So that is our base, but what the question's asking is, what is A? What's our initial culture? So maybe we'll just write this as a preliminary here. So now I need to figure out A, and so I just need to go back up to one or the other of these problems here. Maybe I'll pick this one and plug in my base and figure out my initial culture. So I would have, I'm going to write this as find A, which is my initial. 600 equals A, and then I have 13 to the 6 to the 1/15th is my base, and that's raised to the 15th up here. Okay, so what happens is these reduce out, right? So I'm left with 600 equals A to the 13 over 6. Now multiply both sides by the reciprocal there, and I would get A is approximately, now here I'm going to round, 276.923, so on and so forth. I think your system usually has you round to the nearest hundredth, but we'll look at, or it might be the nearest whole bacteria. You'd have to read what the directions are on that. I'll check that out too. So from what I see in the answer key, they do want you to go out several places. So it would be approximately 276.923 bacteria. So now we're going to look at finding the doubling period. Okay, so we're going to use our doubling time. So if I'm looking at the same format here of an exponential, y equals a b to the x, doubling time is going to have to be y would be twice as much as my initial a. And then my base from before was 13 over 6 to the 1/15th. And that is all raised to the x. So my base is what's in orange there. And my exponential is the other stuff in red. So this is where we kind of adjust those exponents. And we're going to need to solve for the exponent. So we're going to need to use logs. So we would take the log of both sides. You can use natural log or log. I'll do log, common log. So if we take the log of both sides on this one, we would end up with log 2 equals x over 15. I just did 1/15 times x. That's over 1. And then to the log, or times the log of 13 over 6. Okay, because remember that all comes down in front here. I use our log property. So now this 15, just to be clear, I'm going to take and rewrite that just a little bit better so that it's clearly under this whole numerator there. Then I would just multiply both sides by the reciprocal of this log 13 over 6 times 15, or over 15. So multiply both sides by 15 over log 13 over 6. Okay, so my answer for x is going to come out to be 15 log 2 over log 13 over 6, and that is approximately 13.447 and so on and so forth minutes that it takes to double. Now we're going to go ahead and look at the next part. Part C, find the population after 85 minutes. What I have written at the top there is just a rewrite, so we have the information. We'll also need to keep track that our B from before is 13 over 6 to the 1/15th. Don't want to lose track of that. And then we're going to plug in our values. We also know that A from before was 276.923. So we need to use that. And we want to figure out after 85 minutes. So when we use our y equals ab to the x, we're going to plug in A as 276.923. Our B is the 13 over 6 to the 1/15th, and then all of that raised up to the x. So don't forget to put that x in. And in this case, my x is the 85. Okay, so I need to plug that in. So I'm just going to go ahead and replace that. 85. So when I crunch the numbers, I'm just going on my calculator, go 13 divided by 6, enter, and then raise it up, use parentheses, 85 divided by 15, and parentheses, and then calculate that. And I should get, when I do that, I will get about 79.9506. And then just keep that on your calculator, multiply it by 276.923. And you should get 22,140.169 bacteria. There might be a little rounding error here and there. But there should be a margin of error even in the electronic system. If it's real tight and you're getting things wrong, just let me know and I can just send me a quick message. But do say what you want me to adjust, please. That's very helpful when you guys do that. Okay, last part on this long problem, but this is a really good comprehensive review of a lot of different skills. That's why I decided to do one of these. When will the bacteria population reach 1,200? So I have my setup. Again, I have my y equals A, remember, is 276.923. Use that same thing. And my B is 13 over 6 to the 1/15th. And all that raised to the x. Okay, and we want to find out when the bacteria, so we're going to find x, will reach 12,000. So we're going to take that 12,000 and sub it in for y. So I'm going to go ahead and just replace that. And then I need to isolate my exponential, divide both sides by 276.923. Okay, and so on the left hand side I am gonna just round that just for make it look a little cleaner. 43.333, and that will equal 13 over 6 to the x over 15. So remember, this is like x over 1. So I'm just multiplying my exponents there. Then I'm going to use my log properties. So I'm going to take the log of both sides. So log 43.333 equals log 13 over 6 to the x over 15. And this will come down in front. So now I have log 43.333 equals x over 15 log 13 over 6. Make sure that 15 gets down in the denominator. It's just easier if you write it that way in the long run there. And you are going to multiply both sides by 15 over log 13 over 6 so that you can isolate your x. And you end up with x equals 15 times log 43.333 over log 13 over 6. I'm writing all of this out so that you can see what I'm doing, but you can actually just keep it in your calculator. It's probably easier. And then it approximates 73.11764 bacteria. So I hope you found that helpful. It is a long problem, so do your best with it. If it's on a quiz or a test or something, make sure you write out as many steps as you can. That gives you a really good overall of the course. Like if you can do this problem, you're really applying your skills for many, many different topics there. So have a great day.